Okay, hi everyone, and welcome to this new session of the post-base seminar. Just as usual, the reminders, actually, the links to the website, etc., where you can register to have access to the mailing list, the calendar, and I haven't fixed this typo yet, and I'm sorry about it. So for the talk today, you can, as usual, ask questions in the chat, actually, and we'll moderate them and ask. So if you have, Benjamin asked if you have long questions to save them for the end of the talk, but not hesitate to interrupt him, actually, in case you're really stuck because there is, definition you missed or whatever, so that you don't stay stuck. Okay. And just a reminder, this is the schedule of the third chapter of the post-base seminar on PAC-Base, and today is the fifth talk, actually, by Benjamin Guedj. But we still have one more talk in 2 weeks by Badreddin Sherif Abdelatif, so don't miss it as well, actually. So now, and I see that Badr is here, so hi, and I hope you're getting ready because we are preparing our questions. Now, it's my pleasure to introduce Professor Benjamin Guedj, actually. So Benjamin is a research director at INRIA. That's the French Institute for Research in Computer Science, actually, and also a professor at University College London. And actually, Benjamin was very invested, in collaborations between France and UK. Actually, he created, I can't remember the name, but you will make it. Maybe you can remind it, Benjamin, the first INRIA
That's
London team, actually.
that's pretty
Actually,
easy. It's INRIA London.
INRIA
It
London.
says what it does
So
on the tin, right?
Benjamin is also a specialist of PAC-based bound and mutual information bound, actually. He recently wrote with three co-authors a book on generalization bound via PAC-based and information theory, which is a very exciting textbook. So, sorry, I will stop sharing my slide, and now the floor is yours, Benjamin.
Many thanks, Pierre. Good morning, everyone, or good afternoon, depending on where you are. So let me just share my slides. While I'm sharing, let me just pay tribute to Pierre because I actually owe to Pierre to be a specialist of PAC-Base. I started my PhD in February 2011, and the very first person I literally talked to about research was Pierre, and he talked me into this PAC-Base wizardry, and that was nearly 15 years ago now, so it's still going strong. Can you all see my screen?
That was 3 years ago, I'm sorry, actually.
Again?
That was 3 years ago. I can't believe we're that
Nah,
old.
nah, nah, come on. We no longer that young, I'm afraid. Okay, so can you all see my screen? Shall I start, yeah? So I figured I give a talk about two things that really got me excited over the past few years, and they all tie to generalization, obviously. So generalization is really my perk and my core focus in theoretical machine learning, statistical learning theory. But most of generalization bounds, as you've seen in previous talks in that wonderful series, and in particular in the PAC-based chapter, heavily depend on the Kullback-Leibler divergence. And they're also tailored for a number of settings, which in practice are not exactly the kind of settings you're really excited about when you're a machine learner and not a statistician. So I figured I'd give a comprehensive overview of those two, literally, of these two interesting directions, I think. But before that, let me just briefly recap. So for those of you who were at the workshop that we had in May, the post-based workshop, there's a little bit of overlap in some parts of the talks. But my research really sits at the crossroads of statistics, probability, machine learning, a little bit of optimization lately. I like to characterize my research as mathematical foundations of AI, which is both very pompous and very popular with funders. So I'm going to stick with it. And some of the keywords, Pierre mentioned a few already, but obviously PAC-based, generalization bounds. Lately, I've been more and more interested in information theory. I'll say a little bit about the book we've published earlier this year. And during my undergrad and PhDs, I've also worked quite a lot on computational statistics. So there's a number of links also to actual algorithms we derive from the bounds, which I'll touch upon later on in the talk. The generalization theorem, I'm sure most of you, if not all of you, are very familiar with it, but it's all about understanding how you can design learning algorithms that learn well beyond the training data that you're using to actually train the algorithm. And I'll be going into two directions, as I said, replacing the KL divergence with other distances, in particular the Wasserstein distances, and making the bounds tighter by using something we call the comparators. So that's the outline of my talk. I'm just going to spend 10, 12 minutes really trying to set up the scene, in particular, trying to look at what generalization and machine learning actually means. And then I'll focus on those two contributions. So the Wasserstein-based deviation bands, which is a NeurIPS paper from 2023, and the Comparators and Generalization bands bit, which is an iStats paper from 24. I'll close by mentioning a little bit about the book that Pierre very kindly mentioned already, and wrap up by showing actually the links between information theory and PAC-Bayes. Right. So thesis, I'm always defending when I'm talking about generalization is that learning is actually be able to generalize. So this is a kind of a 101 picture. This one's taken from Wikipedia. In machine learning, you're interested in finding boundaries between different stochastic phenomena. And in this particular example, it's very obvious that the black solid line is the actual boundary, and the green solid line is something that will get you very gravely overfitting your objective. And so you don't want to be sticking to the data you've seen already. You want to have some kind of flexibility, and you obviously don't want to train systems which only work on the data they're trained on, but also able to generalize to further data sets. And so memorizing, in that sense, it's kind of the opposite of good generalization. And I like to think of generalization as the ability to perform well on data you have not yet seen. And that's a very vivid, active area of research in statistical learning theory, has been for decades. But I think it's slightly more under the spot since 2017, say, in particular with the deep learning era. And there's this wonderful paper by Misha Belkin and his co-authors that I really refer to pretty much in all of my talks, which is understanding the generalization abilities of neural networks. In particular, we know from statistical theory that the more complex a system, the more prone you are to overfitting. And so there's this trade-off between the capacity of a system, say the number of layers or neurons of a neural network, and its ability to generalize. And nowadays, when you train neural networks, I don't know how many of you in the audience are training neural networks, but it's increasingly easy to see that when you do train those neural networks, you're actually striving for zero training error. And statisticians in the room should just jump, right? I mean, it's literally not what you should have if you're a statistician. But surprisingly, even though you have very low training error, even zero, they actually have fantastic generalization abilities in some contexts. So this is the reference of the book from the paper, sorry, from Misha Belkin and his co-author. And this is what we know from very classical statistical theory, which is the trade-off between the complexity of a set of hypotheses. Don't pay too much attention to the notation yet, but essentially, if the larger the complexity, and the bigger the test risk. If you plot the complexity against the risk, so training risk in dotted line and the test risk in the black solid line, then as the complexity grows, as the number of the layers or neurons grow, as the expressivity of the neural network actually grows, the training risk obviously will go to zero, sometimes very quickly, simply because you can actually interpolate between data points. But what's interesting is that even though the test risk actually goes up after a while, and so for decades now in statistical learning theory, we've been interested about the sweet spots over here. The conjecture of Misha Belkin and his co-author is that this might only be half of the picture. And so this is what the other half might look like. And what's remarkable is that the test risk starts decreasing after reaching a plateau, but it decreases to a point which is lower than than the minimum point in the classical regime. And that might be one of the explanations of the good generalization ability of deep neural networks, even though their capacity gravely violates what we should have from a statistical perspective. So that's yet another motivation to study generalization, still in 2025. Why does it matter? Well, I'm going to fix a little bit of notation here. Those are very classical notation, but please interrupt me if something's not clear. So let's assume we have a sample. I'm going to assume it's ID for now, but we'll relax that assumption later on in the talk. If you assume you have a sample, a supervised sample, we assume we have a loss. For any hypothesis, we can define the empirical error and the actual error, the population error, or the test error, as we will call it, which is simply the expectation of the previous one. And two questions you're asking yourself is, how can you certify that if you have a specific hypothesis H with a good performance on training data, how can you certify that it will have a good performance, a similarly good performance on new unseen data? Or equivalently, when does a low training loss imply a low population loss? And this is all what generalization theory is about. So the typical approach is to bound the generalization gap. So now I'm going to write the least impressive equation of all my talk, which is this one. It's really a simple algebraic game on the different terms of that quantity. So we define the generalization gap to be this gamma function on top of the slide, which is simply the difference between the population error and the empirical error, so the training error. So L minus L hat for any hypothesis H. And we actually want to bound that quantity with the observation that the population error can be rewritten as something which is upper bounded by the empirical error plus a term. And that term is the generalization bound. So hence the name generalization bounds in generalization theory. This ships with a number of flavors, which I think are all worthy of probably many talks. And fortunately, you've had quite a few in this chapter already. But the main four big directions, the main four big flavors, really, of this kind of bounds are bounds which are hypothesis dependent or hypothesis free. So you could have a specific bound for one hypothesis, which is your favorite, the one you're working with, or you might want bounds which are valid for any hypothesis, provided they comply with maybe simple assumptions, for example, abundantness or some formal regularity. It can also depend on the distribution of the data, so the data generation distribution, or it could be completely agnostic to its choice. And again, this leads to very interesting considerations on what kind of algorithms you can deploy and you can train on this kind of bands. And those bands can come in mostly two flavors. They can be in expectation or they can be in deviation, so with arbitrarily large high probabilities. And I'll mostly focus on the latter in this talk, which is really the core of PAC-based. There's a number of bounds which are in expectation, also worthy of discussion. So I'll briefly touch on this later on in the talk as well. I'm going to go quickly on this one because I know Pierre gave a fantastic tutorial at the beginning of the chapter. But in a nutshell, the PAC framework, probably approximately correct framework, due to Valiant in the early 80s, is really all about controlling the probability of making a big mistake. And so you're controlling this with a parameter that I like to call the confidence parameter delta. You can think of this as the probability of being misled by your training set. And I found that interpretation to be remarkably useful in trying to convert new people to PAC-based and to this approach of things in machine learning. So if you're controlling the probability of making a large error, you lower bounding effectively the probability of not making a big mistake. So in other words, to be approximately correct. So we talk about high confidence bounds. And this is the prototypical form of those bounds. With high probability in purple, the generalization gap of any hypothesis H, the blue part, is at most something you can control and in some cases compute. And those are obviously the most interesting cases. So this is what the bounds look like. You can think of this bound term, the Bn and delta term, as some measure of complexity times something which decays as one of the square roots of how many points you have in your sample. And so those bounds are high confidence statements on the tail of the distribution of population losses. And again, I think it's useful to compare those to statistical tests at level 1 minus delta, where you want to assess that the population error does not deviate too much from its empirical counterparts. PAC-based is another layer on this PAC framework. And essentially, it's PAC generalization bands for distributions of a hypothesis rather than just hypothesis, hence the Bayesian part of it. Although we should mention immediately that it's not properly Bayesian, as you already know. But for now, let's just supercharge a little bit the notation. So Qn now denotes a posterior distribution that produces a hypothesis. It's indexed by n because it depends on data. And you might have some prior Q naught. So the two interesting quantities in this context are the empirical error, which is just the expectation with respect to the posterior of the empirical error, and the actual population error, which is the expectation with respect to the posterior again of the population error of some hypothesis H. So because you no longer have hypotheses to compare, but distributions, the most natural way to do so is to use the KL divergence, the Guedj divergence, which is defined on this slide. So what makes PAC-based a POS-based approach? There are three big distributions at play in those bounds, the prior, the posterior, and the delta distribution. So the prior and posterior actually hold on hypotheses, and the data generating distribution appears in the bands in many different places. The big difference between PAC-based bounds and a proper Bayesian inference mechanisms is that the PAC-based bounds will hold typically for any of those three distributions. So the PAC-based prior does not need to be a proper Bayesian prior. The PAC-based posterior is almost never, I mean, it is rarely really a proper Bayesian posterior, and the data generating distribution plays no role in the validity of the band. It does play a role, very crucially, in the tightness of the band, but not on its nature. Whereas in Bayesian statistics, the choice of a prior will largely impact inference. Obviously, the modeling choices, the likelihood you're going to use will largely impact inference as well. And your posterior is uniquely defined by the combination of the previous two. So you have essentially zero flexibility in there. So that's the prototypical PAC-Bayesian band. This one's due to McAllister. The prehistory of PAC-Bayes is due to Bob Williamson, John Schoteller. I'm saying prehistory with John's agreement. I owe to John actually to be at UCL, and he largely underplays the role and the influence he's had on the PAC-based community, but I think it can't be really overstated. And those two fantastic papers from David McAllister, both cold papers at the end of the 90s, really laid the foundations of what's eventually became the PAC-based theory after being formalized by Olivier Cattoni in the early 2000s. So the prototypical bound is that for any prior, any confidence parameter, the probability that for any posterior, the generalization gap is at most the orange bit in that equation is at least 1 minus delta. And so this gives a very usable and ready to deploy algorithm. I'll get back to this in a minute. But essentially, this kind of bounds holds under a number of restrictions. First, it's not written here, but we actually assume the loss to be bounded, which is obviously a limitation. And even though this does not depend on specific choices of prior, posterior, and data generating distribution, in numerical experiments, you can make that bound arbitrarily large if you pick those distributions badly. So how can you use that bound from this kind of prototypical forms where you have the probability of the generalization gap being something which is explicit? You can obviously compute the numerical value of the bound, and that gives you what some people call a numerical certificate of this particular hypothesis, or this particular posterior distribution of our hypothesis. But I think more interestingly, what we could do is actually train new algorithms and derive new hypotheses, so new learning systems. And the generic form for doing this is to look at the distribution Q star, which is actually the argument of the minimum of this quantity, the empirical error evaluated in any posterior plus the value of the bounds. And if you can't use the value of the bound directly, you can use a proxy, you can use an upper bound of that term, you can use an approximation, as many people do. So this kind of turns a learning problem into a very specific optimization problem where you're looking at the optimal distribution over a set of distributions which are absolutely continuous with respect to the prior. Hence, the good choice of the prior is absolutely paramount. And that optimization problem has been solved over the years by a number of people with a number of techniques. In the early stages of my career, I was more interested in MCMC-based algorithms. But lately, the two leading approaches, I would say, are using stochastic gradient descent flavored methods and variational inference. Variational inference, obviously, there's this amazing paper from Pierre in 2016 with James Ridgway, which really also laid down the foundations of using variational inference for deriving PAC-based posteriors. So my point here is that if you're interested in computational statistics and the ways to actually solve this PAC-based problem from a numerical perspective, there's a number of techniques which are of interest. I'll go quickly on this one, but just wanted to mention this result because it's one of the cornerstones of PAC-Bayes, and it's very well known in many different communities. So this is a result which is due independently to Imre Schiza in 75 and Donskoy-Varadhan. This is usually referred to as the Donskoy-Varadhan formula. The statement I'm using here is due to Olivier Cattoni in his brilliant book in 2004, the Saint-Flour note. But this really is the version of the definition of the KL divergence, the Legendre transform of the KL, so to speak. It essentially tells you that the log of the integral of an exponential of any function which is measurable with respect to some prior distribution can be expressed as the supremum of the integral of that same function with respect to another distribution, which will play the role of the posterior, minus the KL between both distributions. And this is really a foundational result. It's also very well used and known as the change of measure formula in many different scientific communities. What's more remarkable is that you actually get a closed form expression for the actual supremum, which is the Gibbs distribution. So a very well-known distribution in mechanical physics and statistics and probability. And never resist the urge of showing the proof because it fits in one slide, which is never the case of my results. But very briefly, the top of the slide is what you want to prove. You write, it's a very simple algebraic manipulations. You write the negative KL of Q and the Gibbs posterior. Then you play with the different terms. And then you remember that the KL is non-negative. So the function that maps Q to minus KL of Q and G can only reach its maximum in Q equals G, and that maximum is equal to 0. And boom, you got the results. So I think it's very elegant and very powerful results, and I'm showing this anytime I have the opportunity. So sorry for that. So sorry for those of you who've seen that proof a million times. But I think what's more interesting in that slide is, let's say now that we leave the realm of probability theory and we enter the gates of machine learning. And let's say we pick an inverse temperature parameter, say lambda, and then you take that phi function to be minus that temperature times the empirical error. Then you write that the Q lambda distribution, which is defined as up to a normalization constant, as the exponential of minus empirical error times a prior. That distribution, so the Gibbs distribution, is actually the distribution that reaches the infimum of that set, which is the set of distributions for which you compute the empirical error plus KL with respect to a prior divided by that temperature. And when you think about this that way, that gives you a form which is very close. For example, when you do penalized regression, this is very similar to the kind of terms you would have if you do lasso, for example. So effectively, you're building distributions which are obtained as irregular rises through the KL of the empirical error. And that kind of justifies one of the terms that Olivier Cattoni used when describing the theory, which is the thermodynamics of machine learning or statistical learning back then. And there you can really see the dynamic arguments and the way when you use those kind of distributions, the way that things interplay and the role that the KL plays in this particular things. Right. Wrapping up that introduction, so generalization bands are safety checks, obviously theoretical, but in many cases you can compute the numerical value of the bands, and you can in particular use these as training objectives, which I think is original in many different settings. Interestingly, many well-known algorithms in machine learning have been rediscovered as solutions and minimizers of PAC-based bands. For example, exponential weights or SVMs can be reformalized that way. There's a number of streams, I would say, in generalization theory. Conservation inequalities, obviously, Radmacher and VC dimensions are the oldest ones. I'm mostly focusing on the late two, so information theoretic bands and PAC-based bands. And that's exactly the topic of the book we've published earlier this year. Right, so the motivation really for the work I'm going to be presenting now is that those classical PAC-based bands actually fall short in a number of settings. They're mathematically elegant, but they're not always very practically useful, especially in machine learning, in context in machine learning, where you have a lot of constraints coming up from the definition of the problem, or the way data is collected, or the size of data, or simply the capacity of the algorithms and neural networks in particular. There's first a geometry mismatch, because the KL divergence ignores the geometry of data space. You can have KL divergences which are really close, where the distributions are actually very far. KL is not proper distance. The KL will blow up also when you pick a posterior. So sorry for the slide change notation. It's just to make sure that you guys are awake in this morning. But rho is actually Q and pi is P. But essentially, If you have posterior which is not absolutely continuous with respect to pi, to the prior, then the KL will blow up and the bound will still hold true, but it will become non-informative. It's absolutely useless to say that the probability of the generalization gap of an algorithm is upper-bounded by plus infinity with probability 1 minus delta. That's true, but useless. And I think even more crucially, the KL does not offer any notion of curvature. And that's a big development in the past few years in machine learning, in particular in generalization theory. So there's a number of papers which have investigated actually replacing the KL with something else. Luc Bégin, Pascal Germain, François Laviolette, and Jean-Philippe Roy have written this amazing paper in 2016 called PAC-Bayesian bounds based on the Rayleigh divergence. And shortly after, with Pierre Alquier, we've written another one, not on Rayleigh divergences, but on F divergences, of which the KL is a specific case, by the way. So that's the first bit. I'm going to talk about. And the second bit is that not all generalization gaps are equal. I started by defining the generalization gap as simply the difference between the population error and the empirical error. But actually, in many cases, difference is not the best choice. Actually, I would argue that it is almost never the best choice, except in very specific cases. And so this gave rise to a number of works as well, still with this paper from Bégin and co-authors, that you can use a different structure to quantify the performance in your problem, and that gives rise to the notion of comparators. So let's move on now to the first contribution, so geometric reformulation of PAC-based bands via Wasserstein distance instead of KL, and rethinking the notion of generalization through comparators instead of just using the difference. So this Wasserstein-based bounds is a joint work with Paul Vialard and Maxime Adouche. Maxime was a PhD student of mine. Paul Vialard is now a researcher at INRIA Rennes, and Umut Shimshikli, who's a researcher at INRIA Paris. This was a nearest paper 2 years ago, and this started with this observation that, as I just said, the classical PAC-based bands actually using the KL can blow up in some cases, will largely be vacuous if you have heavy losses, generating very large values, very large numerical values for the KL, and ignore the geometry of the underlying problem. The Wasserstein distance, so this is the Wasserstein of order 1. We're using the Wasserstein of order 1 in that paper. It does encode some geometry. It does not require absolute continuity if rho, the posterior in this context, is an atomic distribution, then the Wasserstein still exists. So for those of you who are not familiar with the definition of Wasserstein, this gamma set, gamma of rho and pi, is the set of couplings between rho and pi, so the set of probability distributions for which the marginals are exactly rho and pi. So you're looking at the infimum of the expectation of some distance. D characterizes some distance here. So you can just think of the Euclidean distance for now. If you're looking at weights of neural networks, for example, has a hypothesis. And so you're looking at the infimum of that expectation. That gives you the Wasserstein distance. So it's always defined. It does not require absolute continuity. And so what we did in this work was essentially to provide deviation bands, deviation PAC-based bands with this Wasserstein distance, valid in 2 settings. The first one is under a weak moment assumption, so that you can use heavy tail losses. And the second one is when you remove the RID assumption, as I mentioned a few minutes ago. I'm just going to set up a little bit the notation. So the prior is now properly pi and the posterior rho. We have a hypothesis space with some data, that sample S. The hypothesis space is equipped with a metric D. That's important for the rest. And what we do is that we use that sample and we actually break it down into K subsets. It's important that those subsets are disjoint. And then the notation we use is this pi IS. Pi IS is the prior built on all data that you have access to, except for SI. So you remove the bucket SI of the data you're using to actually train that distribution. So that's important because that gives you a possibility to use data-dependent prior via sample splitting. We're using a union bound later on in that paper to provide the bounds, and that's the setting that we adopt. So I'm going to show the first theorem, which is theorem 2 in the paper, which is the batch setting. So if you assume your loss is Lipschitz, with the Lipschitz constant capital L, for any confidence parameters with probability at least one known as delta, we have that the expectation of the population error minus its empirical counterpart, so the actual generalization gap, is upper bounded by two sums. The first one involves the Wasserstein distance between a posterior and the prior learned on all data but the ith bucket. And that has a weight of 2 times the Lipschitz constant times how many points you have in that bucket divided by how many points you have in total, right? That bound is valid for any posterior row. And the second term does not depend on row. It does not depend on the Wasserstein. It's an incompressible term, which involves how many points you have in each bucket and the confidence parameter delta. I should have mentioned this earlier, but as in all bounds in the PAC framework, if you pick delta to be too small, that term blows up. If you pick delta to be too large, then this term vanishes, but obviously the probability of that event becomes dramatically low. So that's the Wasserstein-based PAC-based bound. I think it's interesting to consider a few use cases over there. In particular, if you pick buckets, which are all of the same size, let's say all the buckets are of size 1 over capital K, then you recover the classical rate that you would expect in this kind of bands, in particular in this kind of concentration, even though you didn't have the Wasserstein distance. And having the Wasserstein distance also accounts for some flexibility in the sense that you can compute the Wasserstein between any posterior and the priors learn on subsets of data. So in particular, you can use specific subsets of data to adapt to the particular geometry of the problem. So that's the form of the bound. It's not the most involved form. This is somewhat of a simplified statement, but it gives rise to a training objective, which again is original. Just to give you before giving you the objective, just to give you a flavor of the proof. So in PAC-Bayes, as I said, we have this Danskar-Varadhan, the Legendre transform of the KL, which is one of the cornerstones of most bounds. And we use this as the first step of most bands. In this case, we use a slightly different result. We use the Cantor-Rubinstein duality for the Wasserstein of order 1. We prove a deviation equality. Then we use a control, which is very similar to what Olivier Catoni did to control the difference between population error and training loss. Then you uniformize over all posteriors, and then because we have a sample splitting approach, we take a union bound of K to get the final band. So it's linear in the Wasserstein. It's a deviation bound and is geometry aware in the sense that you can use those different data buckets to enforce some particular geometric properties of the resulting algorithm. So from that bound, you derive this learning objective. If you minimize the right-hand side of that bound, it gives you this expression. So the rho star, the optimal posterior, is obtained by minimizing this expression, the expectation with respect to the posterior of the empirical error, plus the sum of the Wassersteins reweighted depending on how big the buckets are. And an interesting consequence of that is that if you're looking at deterministic posteriors, so deterministic predictors, which means atomic posteriors. Your posterior is just Dirac mass in one specific predictor. So that notation means that you have a hypothesis H, which is indexed by, say, parameters W. So this could be a neural network with parameters W. So weights W. And then if the posterior is a Dirac mass in this exact neural network, then you can rewrite that minimization of the right-hand side theorem 2 as minimizing quantities which involve only the distance between W and Wi, and no longer distributions. So Wasserstein, in that sense, acts as a geometry-aware regularizer. You're effectively promoting solutions which do not depart too much from the prior allocation of weights. You will have noticed that we have this epsilon parameter in front of the sum. I'm going to say a few words about this parameter epsilon. So in the deterministic case, as I said, the Wasserstein between two distributions amounts to the distance between predictors indexed by parameters. And so the theory tells you that you have a weight which is 2 times L, where L is a Lipschitz constant. But then you can use this as simply a parameter. So we effectively learn this. So theory guides you in the sense that tells you it should be of order 2 times L, but actually we use this as a trainable parameter in our algorithms. So you effectively control the trade-off between the empirical risk minimization, which is the first bit, and the geometric regularization, so the proximity to the priors, and that's the second part, the sum. It's in many ways very similar to what you do in more classical Gibbs posterior when you play with the inverse temperature 1 over lambda. So from there, we go to a different setting, which is the online setting, where we now consider that data does not arrive in a batch, it actually arrives sequentially. So you have access to the buckets of data, every one at a time, okay? So we still assume that the loss is L Lipschitz. We assume that the priors satisfy a bounded conditional second moments. So the conditional second moments with respect to the prior are all bounded. And for the sake of simplicity, we're just going to assume that bound is one. And then the bound that we get is a regret bound telling you that the cumulative error, the regret of the sequence of posteriors rho I, is upperbounded by a term which involves the sum of the Wassersteins. So still between rho I and the prior, which is learned on all the data, but the data that you have not yet collected, plus this term with a square root, which is very similar to what we had earlier. So that's really the analogous of the theorem 2 presented a minute ago in the online setting. And from there, we also derive a working algorithm. And that working algorithm controls really the expected regrets of the online learner. As far as we're aware, that's the first online PAC-based band with Wasserstein regularization. Our paper was not the first to prove Wasserstein-based PAC-based generalization bands in the batch setting, but it is in the online one. And that's term 2 times L sum of the Wassersteins that we have over here. This term effectively penalizes deviation from the prior sequence in a geometric way, much more efficiently than you would have with the Kullback-Leiber divergence terms. So that's the corresponding algorithm that we derive from this result. Rho I is chosen as a minimizer of the expectation of the loss on the new point that you've just acquired, plus 2 times the Lipschitz constant times the Wasserstein. So you're effectively departing from the prior. If you have a deterministic learner, so if your posterior is actually just a Dirac mass, then it simply boils down to minimizing the loss plus the distance with respect to the previous parameter that you had in the previous round. So that's online learning with transport regularization, so to speak. And we've evaluated this a number of numerical settings in the paper if you're interested. But I think this kind of opens up nice directions for future work, which is, can we actually couple this with other arguments? So we now have machinery that works if you have heavy tail data or if you have online data. But then what can you do in practice when you want to compare the Wasserstein? What kind of computational difficulties does it poses, and so on and so forth. So in my view, it's really only the beginning of bands which we revolved around the Wasserstein instead of the KL because they're much more amenable to a number of machine learning settings. So the take-home message of this bit is that those bounds are valid, so in deviation for batch and online setting, and the fact that they all feature linearly Wasserstein terms make those very easy to transform into training objectives. And the particular case of deterministic predictors when you have atomic posteriors is worth mentioning as well. Right. Let's now move on, unless you have some questions. But in the interest of time, I'll now jump to the last question. Yeah, Pierre, I see you've unmuted yourself.
I was thinking, just in case, actually, this part is independent from the previous one, if I can jump in and ask just a quick question about the.
Please do.
Because
Absolutely.
you mentioned like the Wasserstein is much more efficient than PAC-Base, and I
And then
mean
KL.
than KL, sorry, than PAC-Base with KL.
Yeah.
I agree that it gives you the possibility to be absolutely careless in the choice of your prior. If you take a prior which
That's
is a
right.
direct, you can still move around it. And
Mhm.
it's a great flexibility. It's nice. But efficiency is meaning something different in the sense that, I would think in terms of statistical efficiency. Question, we know settings where if I use a pack-based bond with the KL, bar posterior will reach a minimax rate, for example. Uh, do you have examples of situations where this is the case with Wasserstein, actually?
That,
Because
that
otherwise,
that's
I'm not convinced of the efficiency. I'm convinced of the flexibility in terms of geometry, etc. But yeah.
that's a fantastic question. No, we don't have yet minimax rates with the Wasserstein. And I think this is literally the next frontier. This is some stuff we're working on at the moment. When I say efficiency, I mean efficiency in two senses. So I agree, the efficiency in the statistical sense is not there yet. The flexibility is certainly there. It's efficient in the sense that, as you say, you can be absolutely careless in picking your prior and posterior. You will still have a bound, you will still have a numerical value of the bound. And in particular, in some cases, you will have bounds which are non-trivial. Okay, so the big thing in bank-based bound these past few years have been to obtain non-vacuous bounds, so bounds for which the numerical value is non-trivial. And you can still obtain this with Wasserstein in cases where the KL would be absolutely trivial, right? So that's yeah,
But something like, because when I mean minimax, I'm not asking you to prove lower bounds or whatever, but I'm just asking, like, assume you're just even trying to do a linear regression with d variables, sample size n, which is d is a constant, it's much smaller than n, etc. It
yeah,
would be interesting to know the order of magnitude of the bound to see if it is asymptotically as tight as KL or not, actually. Because
that's
if you
right.
even in a simple model, actually, that would be interesting.
Yeah, no, I agree. So we have some answers to this in the paper. I didn't put in my slide the numerical experiments because I would have lacked time. But essentially, we have a number of settings, very simple settings, in which the KL is one or more orders of magnitude above the Wasserstein value. And I think that's interesting. There's no universal answer. I'm not claiming that Wasserstein is always superior to KL, right? I'm pretty sure you can find many different settings in which the KL, even numerically, will actually be much tighter than Wasserstein. Um, but it does give you some flexibility in the sense that there are some settings in which you couldn't compute the KL, or if you could, it would very classically blow up. If you have a neural network which is very large, it's really challenging to find settings in which the KL doesn't blow up, right? We often resort to you have a Gaussian distribution, on weights, and then you look at the Gaussian posterior and so on and so forth. So this is very limited. With Wasserstein, you have way more flexibility than that. Does that answer your question? Yeah, cool. Any other questions before I move on to the last bit? Right. So I'm going to talk now about comparators and generalization bands. So this is a bit I've talked about in the May workshops. I'm going to go quickly on this, not as much details. This is work with Frederic Hellström, who was my postdoc at UCL, and this is us and Sunny Valentia at AI Stats 24. So as I said, most generalization bands are about bounding the difference of population loss minus its empirical counterpart. And that's simple, that's easy to interpret, but it's not always tight. So the legitimate question is, can we do better? The short answer is yes, we can do better. So we use that notion of a comparative function. This predates our work. We found occurrences of this notion of comparator as early as 2016. Again, that paper from Guedj and Carthus at AI Stats. But essentially, the comparator function computes a discrepancy between the training and population loss. So one possible comparator is obviously the difference, but you shouldn't be limited really to the difference. The only thing we assume about that comparator function is that it's jointly convex in both its arguments. So this result is taken from the paper from Guedj I just mentioned. If you assume that the loss is bounded, let's say it's bounded by 1 for any comparator delta, so any discrepancy between empirical error and the actual error, the probability of that comparator function being upper bounded by this term in blue is larger than 1 minus delta. So what it tells you is that you have a unified way of writing those bounds. It will always feature the KL. It will always feature log of 1 over the confidence term times some term, in particular this term epsilon delta, depends on the choice of the comparator. But this is a very nice and elegant result that unifies many existing bands. So if you pick that comparator to be the difference, you obtain Macalister's band, which is exactly the band I've shown in the first part of my talk. So that's the result due to David Macalister in the late 90s. If you pick the comparator to be something else, you can pick, for example, what is known as the Catonese density family. So that's delta gamma comparator here. You get a band which is exactly the band that is featured in the works of Olivier Catoni. If you pick the comparator to be the binary KL divergence, so the KL between two Bernoulli distribution of parameters Q and P, which is given by this formula, you get another band, which is very well known in the literature. It's sometimes referred as the MLS band, the Maurer, Langford, and Seeger band, or the small KL PAC-Bayes band, and so on and so forth. So there's a number of comparators that you could use, and the legitimate question is, okay, so what comparator should I use, right, for my specific problem? What is a comparator that actually gives the best results? So when the loss is bounded, we know the answer to that question, and that's been established by this amazing paper by Fung and co-authors in 2021 at INRIA. So Hotite and PAC-Bayes being a small data regime. If you haven't read it, I highly recommend it. And they establish that when the loss is bounded, the best comparator up to a log term is the small KL, so the Bernoulli KL. In this work, we relax the boundedness assumption, and so we extend effectively the results of this paper by Fung et al. So as before, we let the empirical error be the actual PAC-Bayes error. So the expectation was factor posterior of the empirical error of any hypothesis. And then we're going to be using a lot the CGF, so the cumulant generating function of any random variable, which is the log of the exponential of exponential tx, where x is a random variable. We're going to be using that CGF a lot to define a number of conditions under which you can actually extend the results of Fung et al. The first theorem we prove is the average case generalization band. So this is a bound in expectation, not in deviation, if you remember the taxonomy I've described in the first part of the talk. Essentially, if you have this condition, which is essentially a domination condition of some function f, then you know that for all comparators and all posterior absolutely continuous with respect to a reference measure, so prior, we have a result which is very similar to the one of Beja et al. The epsilon delta term is now slightly different. It's expressed as the soup over expectation of random variables for which the distribution actually has mean R. That's what this PR notation means here. But rather than getting fixed on notation too much, I think the idea is that if you have some notion of domination of the comparator function, then you recover that domination term in the bound. To illustrate this, I'm going to show you how you can make this relevant beyond bounded loss. So we use the notion of sub-distribution. If you have a distribution which is sub-Gaussian, you know that it means that this CGF is actually dominated by the CGF of the Gaussian distribution. It's the same for sub-gamma, it's the same for sub-exponential, and so on and so forth. So we define the notion of sub-P, where P is a convenient distribution, and that's highlighted in the next slide. We also use the convex conjugate of the function, which I recall here. So sub-P losses are a set of losses for which you can assert that their CGF is actually dominated by the CGF of distribution P, and so you inherit the properties of that distribution P. In other words, a sub-P loss never has heavier tails than those of P. So if you sub-Gaussian, your tails are lighter than Gaussian tails, and so on and so forth. And we use that notion to remove the boundedness assumption. It's a considerably weaker assumption than assuming that your loss is bounded. And that's the key in proving also all results. The optimal comparator and the bounds are defined in this result. So the short answer, so I'm going a little bit fast because I see I only have a few minutes left. But essentially, we show that the bound is valid for any comparator, and the actual comparator that optimizes that bound is known as the Kramer function, which is given by this blue formula on top of the slide. If you define the bound functional as this b hat quantity, then we have in the lower part of the bounds that the empirical error of any posterior is upper bounded by this bn delta p size, so the bound quantity applied with the comparator, which is the Kramer function, which is upper bounded by the bound functional applied to any comparator. So that proves two things. The first thing it proves is that the Kramer function is indeed the optimal comparator. And the second thing it proves is that you have that bound, which is valid, even though the loss is not bounded when it is sub p. And so that's the main result that we have in that paper. And what's interesting is the connection to generalization from Kramer function. So for those of you who are not familiar with the Kramer function, it's used in probability to characterize the probability of rare events if you have ID data. And so the connection of generalization bands is kind of natural. We kind of realized this when we wrote that paper, because you're effectively trying to characterize the probability of a rare event. You're looking at the probability of your system, not generalizing at all. And you're trying to control and mitigate that probability as well. If you have losses which are of a specific family, in particular the natural exponential families, then we have closed form for the Kramer function. And interestingly, you recover the KL. So if your loss belongs to a natural exponential family, the Kramer function is exactly a KL between two distributions indexed by P and Q. If you have Gaussian distributions with known variances, the best comparator, so still the KL, is given by a closed form, because you know exactly how to compute the KL of two Gaussian distributions with the same variance. If you pick a loss which is bounded, then the Kramer function is the binary KL to recover exactly the previous results, telling you that if your loss is bounded, the best comparator is the binary KL, but it's still also the Kramer function. Sub-Gaussian I've covered. We've also made that computation for sub-Poisson, sub-Gamma, sub-Laplacian. The takeaway message from this slide is essentially that the Kramer function admits a number of closed form. You can particularize what this is in many different learning settings. And depending on the distribution that you pick, which is dominating your loss, then you have also closed form both for the bounds and the comparator. Ultimately, we turn this into training objectives, as we did previously, and that gives rise to a number of different bands. So now we have this generic PAC-based band for sub-P losses, which is a simplified statement, a streamlined version of what we had before. So if you assume your loss is sub-P for any comparator in deviation, we know moving from expectation to deviation, this results. You have this bounds, which tells you that the comparator between empirical and population loss is upper bounded by the KL plus log of epsilon p, depending on the comparator, divided by how many points you have in your data set. I probably will skip that just to make sure I finish on time. But I'll just focus on the main takeaway message, which is that the comparator choice is crucial when you want your generalization band to be tighter. And long story short, the optimal choice when you have a bounded loss is the small KL as a comparator, as established by Fong et al. In 2021. If you don't have a bounded losses, the optimal choice for the comparator is the Kramer function derived from the CGF of the loss. If you have natural exponential families, it all boils down to using the KL again. So the tightest generalization bands, still up to log terms, with controllable moment generating functions obtained with the Kramer function as a comparator function. That's really the main conclusion of the paper. And bear in mind that this Kramer function is reasonably easy to compute in many different settings, and particularly recover already existing bands. So those two directions, switching the KL for another notion of distance or divergence in the case of Wasserstein, and looking at how tight can that generalization gap be, in my view, actually align very neatly, with the objectives of the post-based community and trying to make those theoretical analysis more amenable to modern machine learning, trying to understand how we can reconcile theory and some practice of those bands, in particular when they're used as training objectives. I'll wrap up now by showing first a few open questions. Those are very similar to the open questions I've mentioned back in the workshop in May. Unfortunately, we haven't solved any of them yet. Essentially, what's interesting is that there's, as I said, always this log term. It's optimal up to a log term. So as always, can we eliminate that log slack? Can you actually derive conditional neutral information bands? So instead of using the KL, can we use more information theoretic quantities? I would add another one to this, which is, can we actually have a similar approach using Wasserstein instead of KL? And does it change actually that assumption of sub P? In practice, calibrating those quantities is hard. We've run a number of experiments with Frederic, but it's not always been conclusive. So there's also, I think, quite a lot of work to do in that direction. Right. Trying to unify a little bit all of those contributions. Let me just say a few words. Just have a couple slides on these links between information theory and PAC-Bayes. So this is the book that we've published earlier this year in Foundation Trends in Machine Learning. This joint work with Fredrik Hellström, so my former postdoc, Giuseppe Durisi, who's a professor at KTH in Sweden, and was also the PhD advisor of Fredrik, and Max Radzinski, who's a professor at University of Illinois. And so in that book, we've essentially tried to cover and unify all streams of generalization, in particular from information theory and PAC-Bayes. And essentially, we wanted to illustrate that there's obviously very deep links between both. And we're not the first one to point this out, obviously. This has been long known in the community, but I think a reference textbook on the matter was lacking, which is why we wrote this. But the two approaches are very close. So PAC-Bayes bands really focus on relating predictors to prior and posteriors. It's a randomized approach in the sense that you're more focused on distributions of a hypothesis rather than just hypothesis. When you're in information theory, you want to relate data to algorithm, in particular to their complexity and capacity. So both approaches rely on three steps, which are actually very common, even though using different mathematical machinery. But you always want to control some form of exponential moments of the loss, or the differences of the loss, or the comparators of the loss, depending on how advanced you are. You always want to perform some way of change of measure. When you're doing KL, it's the Legendre transform of the KL, so the Donsky-Varda and César formula. If you're using Wasserstein, it's the Kantorowicz-Rubinstein duality formula and so on and so forth. But you always kind of want to do a change of measure relating the prior and the posterior distributions. And then using concentration arguments to provide a bound. So we show this pattern both in information theory and PAC-Bayes with a number of examples. We have one deep learning, we have one on algorithmic stability, which is a very popular approach, in particular in information theoretic in IT. And we hope this to be one of the foundations for modern generalization theory. The field is progressing fast. PAC-Bayes is not that old as a theory. It's almost 30 years old now, but that's not that much when you compare to VC or Rademacher approaches. So the field has been progressing immensely over the past decades, and we think we know seeing a lot of convergence coming in from the community, and communities in particular. I remember very eye-opening discussions, in particular with Jeremias a few years back, when we were discussing essentially the same result coming from different communities with different names and different papers. And I think we know getting there, and we know building a framework in which all of this is actually seen as it is, that is really progressing the idea of generalization. So PAC-Bayes compares the learner's average performance under a posterior and a prior. In IT, you would quantify how much the algorithm actually reveals about the training data. But interestingly, there's a number of settings in which you can write PAC-Bayes bands as IT bands with the right choice of distribution. So we have an abundance of those cases in the book. The book is nearly 250 pages, so I'm not going to comment on this. I'll refer to the book for lack of time because I'm already overrunning a little bit. The last thought I'd like to close on is that I see PAC-Bayes as a constructive approach, right? Because it does suggest training objectives. When you have a bound, If you can numerically evaluate that bound or even a proxy of that bound, then it gives you a natural training objectives. And now, as I said, in many different cases, those training objectives actually coincide with existing algorithms and existing training objectives, such as SVMs or exponential weights. Uh, Information theory, on the other hand, is more of a diagnostic approach, in my view, because it measures complexity, it measures stability of algorithms, and you're trying to look at the capacity, in the end, of those algorithms and trying to relate this to a measure of performance. So, in many ways, it's complementary. That gives you two complementary approaches on generalization, and hopefully the book is doing a convincing job in tying those two together. The practical lessons, if you're more into practice than theory, is that depending on the concentration regimes, like the different geometry you might be using, either the KL or the Wasserstein or another distance or divergence, depending on the data behavior, depending on abundantness assumption, and so on and so forth, you might have a number of, say, frameworks at your disposal. So you can have KL-based bounds for light tail data. You can have the equivalent for heavy tail data. This is, for example, the work we did with Pierre a few years back, or the one I've presented with the Wasserstein. There's also the robustification of the loss due to Olivier Catoni with truncation. If you use Wasserstein, you kind of replace that KL notion by a transport cost, and so on and so forth. So each of those regimes suggests some kind of a training principle. This is very hand wavy, but I thought it'd be a nice conclusion, and maybe also opening up to questions. If you're using the KL, you're kind of prone to, you kind of bias towards exponential posteriors, such as Gibbs posteriors. If you're using a way to train a la Catoni, then you're mostly looking at variance controlled losses. If you're using the Wasserstein results are presented in the first part, you're more prone to pay attention to the geometry of your problem, in particular in sense of data, and so on and so forth. So this kind of paints, taxonomy of the different strategies in PAC-Bayes. And I like to think of this as a continuum. It's not conflicting, it's not contradictory. It really forms a continuum from information theoretic to a slightly more geometric way to perform machine learning. And hopefully this can be seen as one toolbox, useful both to people working in theory and people working in more practical machine learning. And on this, I'll end there. Thank you very much.
Thank you, Benjamin. Are there any questions apart from the one I asked earlier?
I do have a question, or maybe like I would like to hear your thoughts, Benjamin. Can you hear
Hey,
me?
Andres. Yeah, I can hear you. Nice to see you. No,
Yes.
actually, I can hear you, but I can't see you. But I
Okay,
can
okay.
hear you fine. Yeah, that's fine.
Yes, maybe sorry. So my point is like, one of the main issues or all these bounds is the fact that at the end you have to define these posteriors over a high dimensional
Yeah.
space. Do you have any idea of, because um, for the KL, we have a clear idea that it really blows up. No,
Mhm.
you have high dimension, especially when the posteriors that are tractable, like this kind of mean field posteriors that fully factorize, they end up blowing up the KL term.
Yeah.
So what is your impression if in the use of Wasserstein's distances?
So that's a super interesting question. I think I have two comments on this. I'm afraid I don't have a good answer, but at least I have two comments. So the first one is those are bounds, right? And this is something I'm debating regularly with my co-authors and my students in particular. It's not because the bound is loose or appears very not tight, and then it's not useful. In particular, in the sense that you still want to use this as a training objective. So the fact that because you have very large multidimensional objects, the actual terms in the band can blow up doesn't mean that the band is not useful as a training objective, right?
Mm.
It might be an artifact of the band. And maybe the KL exhibits an interesting behavior because it helps you find the right minimum points of those training objectives. But in practice, it overshoots and it overcompensates so gravely the tiny differences in posteriors that it's very rare that it will be actually numerically non-vacuous, right?
Yeah.
So that's the first element of response. The second one is I don't know yet, because that's only one paper we did, and we do comprehensive studies, on numerical implementations of Wasserstein. My intuition is that in the cases where the KL is actually very vacuous, the Wasserstein is at least comparable or slightly better. It doesn't mean that in some cases, as I said to Pierre earlier in the talk, you might imagine some cases where the KL will be actually very tight, and the Wasserstein will be, at best of the same order of magnitude or even larger. So the point is, I don't think there's a good answer to one of those strategies, either the KL or the Wasserstein or the F divergences or something else, is uniformly better from a numerical perspective. What I think I'm really interested in is, does it give you an algorithm that leads to good predictors? A good predictor is a predictor. I haven't talked about test bounds, but if you compute those predictors as solutions of PAC-based bands, and then you look at test bands, they actually do well, right? Some of the predictors are actually quite performant, and in practice, they have very good results. The band doesn't really tell you that, right?
Yeah.
And if I go back also to remember that plot from Misha Belkin and his co-author, again, this is an upper band, right? So it's very possible that in this particular plot, if I were to plot the bounds, I would have a straight line which is very high, in that plot, and doesn't tell you anything about this double descent phenomena. But still, if it has a dip on the right side of the plot, it might lead to solutions which actually have a good complexity, which are good generalization, and the band won't really tell you that. Does that answer your question?
Yeah. I think it provides a very nice perspective. Thank you. Yeah.
And
Yeah.
I would like to jump in because it's,
Yeah.
I mean, we discussed that in person already a few times, Benjamin, but that's a slight disagreement I have on the sense that, okay, I agree, it's cool if when you minimize a bound, it gives you a good predictor in practice.
Yeah. Yeah.
I don't think that if you minimize a bound, which is very loose and gives you a super good predictor, I don't think we have any understanding of what is happening. Actually, I don't think that it can be seen as PAC-Bayesian thing explaining that it works. Actually, in a sense, like I really like, for example, like Carolina and Dan's paper on non-vacuous bound,
Yeah.
because there's the will to show that it's not, it doesn't have to be always the case, and sometimes you have non-vacuous bound. For me, one of the reasons, because that's very much because I'm a statistician and not a machine learning person. Probably I have this feeling more and more, but like if you minimize the PAC-based bond and you obtain something which is good, for me, it means also together with the empirical bounds, you have the oracle bounds, which can give you
Yeah.
rate of convergence. And in a sense, it means that you're minimizing something which already gives you the correct rate of convergence, but that does not have the correct constant, because actually, when you minimize the bond to take care of the exact constant, etc., it takes, and sometimes even maybe it's possible that the original PAC-based bond is quite loose already. So for me, it's something that will reach the correct rate of convergence, but you don't have the tight constant. So then in this case, you have a bound which, when you minimize it, will be good, but might be indeed vacuous on a specific data set, actually. So
I agree.
that's exactly what, and sorry if I come back
Yeah.
to you always with this question about the Wasserstein. In a sense, what I want to understand, because I totally trust you that it might be order of magnitudes better than the KL in some specific data set. But my question is the statistical question. If you let the sample size tend to infinity, will it always be the case? Because you have also a minimax rate of your bound. So you have like the same rates than the PAC base, but with a better constant? Or is it just an artifact due to the fact that the pack base is suboptimal in terms of constants, but it will catch up, for example, which I believe is a valid information if you're looking for scaling laws or things like that, actually.
Yeah, I agree. I was just about to mention scaling laws because I think in this kind of context, it still provides some useful information. Just to go back to your earlier points, so I agree, and I'm always, a little bit cautious when I see other statements such as, PAC-based does explain 100% the generalization of X, right? I don't think that's always true. But that's certainly, what we're striving for. And one very toy example is that if you have a band which is super tight, okay, I have some bands which, for example, are super tight for neural networks, with specific architecture, 2 layers, and so on and so forth. If I'm taking that bound and I, add a constant 10 to the power 15 on both sides of the inequality, the band is still the same, right? And I can still use this as a training objective. It will give me the exact same result. Okay, so the band is very loose, but the resulting algorithm is actually very good, right? So that's obviously something we're missing here. And in many cases, this is a toy example because I know the band is great and then I just artificially make it blow up. But in general, it's very hard to understand whether we have the right order of magnitude, right? So that's to go back to your initial point. On Wasserstein, yeah, go ahead.
I disagree on that in the sense that if you take the oracle bound, actually, you write an oracle version of your Wasserstein bound, then it's quite, you take a specific problem, linear regression or logistic regression, where you know the minimax rate actually, and you just try to play with the prior and your posterior in your bound until you see if you can reach this rate or not. Actually. And if you can't manage to do it, you try to probe a lower bound. But I don't think it's a very challenging question actually. It's more a question of checking things.
Yeah, but the issue is that it's only valid in very simple settings, as you say, right? I mean, you can do this for a linear regression problem. Can you really do this, for an arbitrarily large neural network with unbounded losses? I'm not sure.
Yeah, but like if you try to do it for linear regression, and if you cannot do it, then it will shed, some doubt on.
No. Yeah, on that I agree.
If you do it, I agree. If you do it to linear regression, then you will have to do it for logistic regression, then maybe for additive model and single index models. And we know people who did that with PAC-based and who can do it again with the Wasserstein. It can be like many, many papers, but I think that in a sense, it would add, it's not like a criticism, it's more like saying it would probably convince more people if you can come up with a couple of models that are well known where you can prove actually already that you recover the minimax rate of convergence. Because even if you cannot recover it, it might give you ideas to improve the bound that will actually recover it ultimately. So I think it's.
I agree. Yeah. Right. Any other questions?
I have my own obsessions actually. That's minimax rate because like after 5 sessions of this chapter 3, people already understood that actually I'm only a fake Bayesian. That's the title that was once given to me by a true Bayesian. But I like frequentist checks of using rates of convergence. But I mean, I think it's great. Honestly, to be fair, I have no doubts that it should be the case, actually, that if you take, linear regression in a small dimension and later high dimension, you should be able to recover optimal rates with this, actually. So that's, but it would be nice to have this written because actually it would probably convince also people doing theoretical stats, etc. So, okay, now
I think
I find that I expose my obsessions in front of everybody. So if someone has a nice question.
My takeaway of this is that frequentist is maybe the last stage of post-Bayes, which is interesting.
Yeah.
That's I'm so Bayesian that I don't even need a prior anymore. Well, if there are no more questions, I will just talk 1 minute to conclude the talk. And then if you have another question coming meanwhile, don't hesitate to ask it. But first, thanks again, Benjamin, for your talk. Very, very nice to follow. And I must say, I knew probably an earlier version on the bound of Wasserstein because actually I didn't know the new version of this bound, but I was not aware of the second part actually on the comparator. So it's very nice.
Thanks, man.
And then also, thanks again, Benjamin. And
Thanks.
don't miss Badreddin's talk in 2 weeks. And then that would be the end of the 3rd chapter. And then we will have a Christmas break and we'll see, hopefully, Santa Claus will come up with the 4th chapter for 2026, actually.